So what we're going to do here today is we're going to be deriving the Fenske equation for the minimum number of stages in a distillation column. So what I have here are just a couple stages that would be in the stripping stage of our distillation column, and we have our reboiler here at the very bottom. Now, what we assume when deriving this Fenske equation is that we are at infinite reflux, meaning that we don't have feed, all the condensate is refluxed through the distillation column, and we also have no bottoms exiting. So it's kind of just an infinite loop in your distillation column where you're not really producing anything. So that's what this demarcation is. We have infinite reflux, meaning that our bottoms flow rate is 0. But what we have present in our, I'll do this in a different color so this doesn't look like a feed or a flow or anything. What we will have in here is something for, well, let me write this out. What we're going to have is this X for the heavy key and this X for the light key. Now, the heavy key and light key are kind of, well, the reason why they're called key is, take into example, maybe we have a 3-component distillation. And say that we want to be distilling in this area here. Oh no, I did that. Basically, this A, if this was on order of volatility, maybe this was more volatile here and less volatile here. This A would be our light key, and this B would be our heavy key. The light key is the lightest component that shows up in the bottoms of your distillation column, whereas the heavy key is the heaviest component that shows up in the distillate portion of your it's the lightest component. Oh my lord. It's the heaviest component that shows up in the distillate exiting your total condenser at the top of your distillation column. So these are just some basic terms for us to continue our derivation. So what I'm going to say here is that this is the X, the liquid mole composition of our heavy key at the bottoms, and this is the same thing for the light key at our bottoms. Now, these two don't necessarily add up to 1 because, like I said, there could be a multi-component distillation going on, so you might have a third term here that isn't present as the heavy key or the light key. Now, in a previous video, I brought up the idea of having a volatility coefficient, and this is basically your ratio of your this is the ratio of your X, your liquid mole component, to your vapor mole component. So we can make this relationship for our heavy key and light key. So we say something like the Y for our light key at the bottom is equal to the volatility ratio of the light key times the X of your light key at the bottom. And the same can be said for the heavy key. So something like this, heavy key, X light key, or heavy key bottom. So this just follows that relationship, this K equals Y over X. Now, what we might want to do here is go ahead and divide these two relationships we've just derived. So we're going to have something like this. We are going to have a Y for the light key, Y for the heavy key for the bottoms is equal to, and now if you remember the definition of relative volatility, it is the partition coefficients. These are what these are called. The partition coefficients, it is the ratio of partition coefficients to a reference partition coefficient. So this alpha, and I'm going to call this alpha light key. And the reason I'll call it alpha light key is because in almost every case, you're going to use the heavy key as your reference coefficient. So this K for the heavy key is your reference, and the light key is what is being divided by your reference coefficient. So that's what the definition will be for that going on. Then we also do the same for the light key and heavy key of the liquid phase at the bottom. So here is the next step. So the next set of relationships we're going to derive comes from this idea that because we have an infinite reflux, our vapor flow rate is going to be equal to our liquid flow rate. And that is referring to these two streams here, and that'll also refer to this stream and this stream. And so the idea behind that, and the idea behind saying this, is that we can go ahead and pull something like the vapor flow rate times the vapor mole fraction of the light key coming from the bottoms has to be equal to the liquid flow rate times the liquid mole fraction of the light key coming from stage N. And so I'm going to call this stage B for bottoms, and then this is stage N over here. So basically we're saying whatever the vapor moles leaving our reboiler, the rate of that must equal the rate of liquid influxing into our reboiler, and thus the moles leaving and entering must also be balanced. And so we can also say the same thing for the heavy key. So in the same way, VYHK of the bottoms is equal to LX heavy key from stage N. So here is the next set of relationships. So similar to what we did before, let's go ahead and divide this once again. So I'm actually going to reverse the order, and you'll see why in a minute. But basically what we're going to have is our liquids are going to cancel out and our vapors are going to cancel out. So get rid of these. And so X of our light key over X of our heavy key from stage N is equal to Y of our light key over Y of our heavy key from the bottoms. But we also notice that this relationship is already predefined, and we said that that's also equal to the alpha of the light key times X light key over X heavy key of the bottoms. So through these couple of assumptions that we've made, we have related the liquid mole fraction ratio from stage N to the liquid mole fraction ratio from the bottoms. So if we keep doing this, and let's say that instead of now going from our bottom stage to our end stage, why don't we group together our bottoms and end stage and start looking at these flows from the n-1 stage, to and from the n-1 stage. Well, what you're going to find when you run through this whole thing again is that, so now we have this light key, X heavy key from the n-1 stage now. What you're going to find is that you're basically going to repeat this, but you're going to be doing, where is it? You're going to be doing this multiplication twice for the relative volatility. So what you're going to end up with is alpha squared times your light key, and then your X light key, X heavy key from the bottoms. So now you realize that with each stage that we overcome and derive for, we keep adding an increment to this exponent that is the same number of stages that we have encapsulated. So if we were to say that we want to go all the way from the top, so if we were to say that we are going all the way up to the condenser where our distillate is exiting. What we will find is that we're going to have this relative volatility to the nth power, n being the number of stages. So this is the number of stages. I don't want to draw that there because I'm going to write the rest of it there. Times x of your light key, x of your heavy key at the bottoms. And this, in essence, is your Fenske equation. So what you can do here is now you can specify your variables. What recovery do you want up at your condenser? What recovery do you want at the bottoms? And having calculated this and getting literature values for your relative volatilities for whatever component you're using, you are able to get this n, this number of stages, to determine the minimum number of stages that you need to design your column for to achieve your expected recovery and other things that you may specify within your distillation column. So then the final step to get the Fenske equation in its final form is just going to be solving for n. So we're going to divide, so x light key, x heavy key, split over the same thing for the bottoms. And you will be taking you would have to take the log of this. So right, because you would need to, you want to separate out this n over here. And then this is over log alpha of the light key. And this is how you would isolate your number of stages. So this equation here is the Fenske equation for the minimum number of stages in a distillation column.